Hello, everyone. Good afternoon. We have Akshay and Lakshmikant here. Hello, Akshay.
Hello, sir.
Hello, yeah. So, any questions? I think you posted a couple of questions online.
Hello, sir.
Sir, posted 3 questions.
Yes. Lakshmikant? Okay, Bhunesh is having some comments. All right. Okay. I heard the name. I don't know. Yeah. Bhunesh, any questions? Please start. Guys, can you track? I think Jinal or Saurabh or someone, can you track the YouTube link also? All right.
Yes, sir.
There are 4 people now on the YouTube link. All right. Good. Akshay, I think let's start with you then, because you've already posted the questions.
Okay.
And yeah, so the first question I think was about we have shifted from planar to FinFETs. Are we still using high K dielectrics as a gate material? Okay. Well, that's a tricky question because this is a very proprietary technology. I'm not certain actually. I'm not absolutely sure whether it is silicon dioxide or it is the combination. Most likely, I think it will be some silicon oxynitride and so on. Okay, it will not be pure silicon oxide. The reason for that is, when you introduce some oxynitride, the index slightly increases and there are some better properties. Epsilon increases slightly. Okay, so but I think, I'm not absolutely sure what exactly is the gate material right now. I must confess. But let me just try to put that into context for everybody. So Akshay's question was actually about the gate material. So let's say you have the planar MOSFET, right? So we have an oxide here, and we said that we finished 8 weeks, right? Or 10 weeks, close to 10 weeks now. So yeah, this is my gate material, and this is my silicon dioxide. And over the years, we talked about the scaling, right? Essentially, scaling of MOSFETs, which essentially makes them smaller and faster and better and so on, right? So this is a scaled transistor. Okay, when you scale the transistors, why do we scale the transistors, by the way? Anybody? Bhunesh? Or it might be actually, there might be a lag. I think Bhunesh is on the YouTube chat. Anyone can tell me why we scale a transistor?
To increase the integration density, increase the performance.
Okay.
Make them more power efficient.
Right. So there are lots of benefits, right? You make them more power efficient, you increase the density, right? Those are the main things. And you saw the metrics that we can actually compute, right? The drive current increases, the delay reduces, the power consumption reduces, and so on. So this we discussed, I think, in week 10. I'm not certain. Week 10, I think, right? Where we talked about the scaling.
Yes.
Right. Okay, good. So yeah, there are a lot of benefits to it. And actually, if you look at Hemant. So Hemant, there's a lot of lag because, Bhunesh, because I think you are on YouTube, you're not on the Zoom link. So there's a lot of lag. I'm not able to, I think, talk to you in real time. It's all right. Okay. So yeah, we are increasing the performance by actually reducing the size. And that's the whole story effect, right? If you take the older generation technologies and make them smaller, you have a better transistor. Okay. And more cheaper transistors. So it was a dream come true for all of us, in semiconductor industry. Okay. So, that ran into problems. And what were the problems? Lakshmikant, what was the problem when we tried to scale a transistor? Moore's law. Moore's law, Moore's law is what captures this, the increasing density of all these transistors is captured by Moore's law. Gordon Moore essentially said that the number of transistors would double every 3 years and so on. Okay, that's Moore's law. But the issue is that the thickness of the oxide, eventually, thickness of oxide became very, very small. Very small. How small?
As thin as 1 angstrom?
No, 1 angstrom you cannot.
Nanometer?
About a nanometer, 1 nanometer. Because even the atomic dimensions, atomic bond lengths are in the scale of 3 angstroms and so on. Okay. So 1 angstrom is not reasonable, but essentially we ended up with a thin layer. 1 nanometer would correspond to roughly 5 to 6, or maybe 4 to 5 only. 4 to 5 atomic layers of SiO2. So extremely thin substrates. Okay. When you go into such very thin thickness of oxides, you can imagine that there will be tunneling. Okay. So what is tunneling? Well, essentially, if you put an oxide, right? For example, I took let's say, okay, like take a metal wire. Okay. Attach a metal wire to two pieces of a big piece of glass. Okay. Let's say this is my glass and this is my metal, let's say copper wire, Cu wire. And this is my glass. Do you expect conduction? We don't, because it's glass. Glass is an insulator and so on, right? If you attach it like this, there should not be any conduction. We have to have a continuous metal piece. But it so happens, so this, if you look at it in terms of energy band diagram, what you will see is, you will see that glass is going to be it has a large band gap. This is EC and EV of glass. And this EC minus EV is about 9 EV, right? This is about, this energy band gap is 9 EV. And other side, let's say you have metal EFN and EF metal, right? EFM, I'll call it. So in effect, there should not be any conduction. But if you reduce the thickness of this, thickness of oxide, if I make it 1 nanometer, very, very thin oxide, if you put it, it is going to conduct, even though there is this energy barrier, right? You see this is an energy barrier. Even though this energy barrier exists, because the thickness is small, we'll have tunneling. I think in one of these assignments, we actually talked about it. Okay. You can try to look at how it is. Okay. What is the tunneling probability? We talked about. I think it will basically depend on the tunneling coefficient, and it will be something like exponential minus alpha d. I don't know which first assignment we talked about, Vinod, right? This is the thickness.
Yes, sir. First assignment.
First assignment, is it exponential minus exponential alpha d? So if d is very large, then very little gets through. The tunneling current, very small amount will be there. But if d is small, the transmission through this will effectively be large. Okay, large amount of current can tunnel through. Current can tunnel. Okay. All right. So because of this, when we scaled the MOSFETs, the thickness of this oxide became very, very small. And then we started seeing that the leakage current was increasing. Why is that a problem? Hemant, you're answering a lot of questions. Well, yeah, quantum tunneling you talked about, and then there are quantum effects coming to picture. Yes. Well, I mean, this is a quantum effect, right? The quantum tunneling is effectively a quantum effect. In classical physics, there's no analog of it. If I try to run across a wall, we can't run through the wall. We are classical objects, and if we try to go across the wall, we cannot go other side. We'll simply break our head. That's it. Right? But an electron can, in principle, go. There's a finite probability that electron can actually go through that. Okay, the wall is a tunnel in a way, tunnel, the barrier, right? And then you can tunnel through that. Okay, so we had this problem, right? So how did we solve this? I'm trying to review some of it for you guys. So let's say this leakage current became high, and what is the problem if leakage current increases? Akshay?
There would be a significant leakage power.
Yes. So what?
A logic operations get affected.
Logic operations get affected because, basically we talked about ion by I of. Leakage current means I of is increasing. Okay,
Yes.
That's one reason. Another simpler way of thinking about it is a MOS capacitor is a heart of a MOSFET, right? So MOS capacitor or any capacitor, it works on a principle that you have two metals like this, separated by insulator, metal and metal, this is an insulator. Let's say SiO2 insulator, right? Why do I call it SiO2? Let's call it a insulator or yeah, insulator. So if your insulator is not good now, it is actually leaking. If it's a leaky insulator, what happens to the capacitance? Right? So all of MOS physics is essentially you are putting positive charges or negative charges on one plate, opposite charge will happen on the other plate. Okay. NMOS electrons will accumulate, will be NMOS transistors, NMOSFET, electrons will be the charge carriers, PMOSFET, holes will be the charge carriers. So now, if you have a leaky insulator, what happens? Hemant? Bhuvanesh is silent. After a reference to Ponni and Selvan, he is not saying anything. Well, did it release? Okay, I don't know. I'm not following that, so I'm not certain. Okay, yeah. And what happens if you have an insulator?
Capacitor action is lost.
Exactly. Okay, the capacitance action is lost. There will also be some conduction, and because of that, it will not work like an efficient MOS device. All right. No band bending. Will there be band bending? Well, I mean, I think as long as there's an electric field, right? Okay, I mean, if you say that it's a completely shorting, of course, then yeah, there is no band bending. I agree with you, Bhuvanesh. But if it is not yet fully shorted, there can be some leakage. Okay, there is some gradient in the electric field. Okay, I assume, Bhuvanesh, you're talking about the gradient in the bands in this way, right? We show this very common way. So the field is actually in this direction, and then let's say this is positive charge, and then there will be some band bending on this side, right? Initially, okay, we think of something like this. Okay, initially a PMOS, bulk P-type substrate becomes an inverted channel, right? So this band bending happens because of electric field. You're right, partly that if you have a very strong leakage and essentially you have it becomes like a completely transparent. There's no voltage drop across this, then there is no band bending. But in effect, you'll never have a perfect metal here. You'll also have some resistance, and there'll be some voltage drop across that. So there will be some band bending. Okay, Bhuvanesh, I won't say that exactly it is no band bending, but yeah. Okay, all right. So now to solve this issue of leakage, right? So basically, this insulator has become very, very thin over time. When it becomes so thin, we have to come up with some solution to that. It doesn't work, right? What do we do? Bhuvanesh? What is the solution for a leaky insulator?
Replace the material itself, which is compatible with the silicon fabrication process.
Yes. So the idea is, if you have a thin material of SiO2, we made it thin because we wanted to increase the capacitive control, COX. COX is equal to epsilon oxide divided by TOX. Okay. If as TOX reduces, COX increases. And we like that. We want greater capacitive control because Q inversion equal to COX into VG minus VT. VT and whatever, I don't know, VT not whatever, I don't know what we called it last year. Okay. Yeah. Basically, we want this so that we get a larger inversion charge and better capacitive control. Now, the problem with this was, I'm sorry, I'm taking a long detour, but I'm just trying to recap for everyone. Okay. If you have any questions, feel free to jump in. I mean, you can interrupt me anytime you want. Okay. Yeah. So what we did was, what semiconductor industry rather did was replace this oxide with a thicker dielectric. Okay. So, and that essentially is high K dielectric. Okay. It could be hafnium oxide, hafnium oxide, or there are various other combinations of it. Okay. It's not a simple dielectric anymore because there are so many other issues that have to be solved. Okay. So The idea was now you will have gate, C gate, I'll call it, okay, instead of C oxide, is epsilon high K divided by thickness of T high K. Okay, the idea was if you are able to change epsilon of silicon dioxide was 3.9. If you replace that with epsilon of 2.25, let's say, epsilon of hafnium, let's say high K, HK is 25. If I increase my dielectric constant, then effectively I can have a much thicker dielectric and still have the same gate capacitance. Okay. So if I have a thick dielectric, I can avoid the leakage. Okay. You follow that? So both have, so basically we can define what is known as equivalent oxide thickness, EOT, equivalent oxide thickness. So basically epsilon of oxide divided by epsilon of high K into thickness of the dielectric. Okay. I remember this formula just by noting that the equivalent oxide will be much smaller than the dielectric thickness. And to get that, I should be smaller dielectric constant divided by the larger dielectric constant. Okay. So if you do that, I'm able to get lesser, equivalent oxide thickness, which is very, very small. But physical thickness of the dielectric is large. And so we can have, we have less of leakage. And this is what Intel did in 2007. Okay. In 2007, Intel introduced high K metal gate. That's what I think I talked about in week 10. I think I mentioned this. Okay. Now, Akshay's question was, can somebody check it online? Jinals or somebody, can you check what exactly is the dielectric in FinFET? But I think we'll have to go back and look at IEDM papers. I don't think this will be so easily discussed. And even that will not be pure. I think I won't expect it to be pure silicon dioxide. Okay. But that's something we can check. And Akshay will write to you about this. Okay.
Sure, sir. So even though the materials themselves are proprietary, there are still some measurement techniques to know the exact chemical composition, right?
Oh, of course. So, yeah, I mean, this can be done. I know that it was actually done. Let's say when the transistor came out in 2007, some people have actually looked at the cross sections of it. They have cut it open and then look at the cross section of the transistor and then look at the material distribution, and all that was done. But it involves quite a bit of expense, and people do it, of course. You will not know exactly the conditions and everything, but you can more or less guess. And over time, I think it comes out. It's not that nothing comes out. But I'm not certain, so I don't want to give you an answer one way or the other. Yeah, we'll check it. Okay. So, and then after that, in 2011, Intel went to FinFET. The reason was high K was good for a couple of generations. To the 45 nanometer and 32 nanometer, they were okay. Even 28, they had high K. But then it became limiting. So Intel introduced what is known as FinFET in 2011. Okay. They went from a planar MOSFET to, let's say from this planar MOSFET, they went into a three-dimensional MOSFET so that they can have better gate control now. Now the oxide is all around like this insulator. And then there is a metal around that like this. This is a metal. Okay. Akshay's question was whether, this oxide and metal, now if you went to FinFET, did they go back to silicon dioxide? Why would they like to go back to silicon dioxide? Because, silicon dioxide is a great interface. It has very less defects. So it's easier to manufacture. Okay. And even in terms of the aspect ratios and all, if you have thin dielectric, that makes sense. So that's one reason to have actually silicon dioxide. And then, but the issue was, depends on what kind of metal is used around and all that. Okay. Is it polysilicon or metal, or is it a polysilicon gate or a metal gate? All that, at least from, yeah. Sorry? Yeah. Someone is speaking. Someone is speaking. I'm sorry. ABC? I don't know your name. Sorry. You're trying to say something? Lakshmikant, yeah, please.
You're talking about insulator. Is this insulator is a perfect insulator, acting like a perfect insulator, or it has some defects?
Well, see, there will never be a perfect insulator. The reason is there can be some defect. For example, if I talk of silicon dioxide, right? If I talk of silicon here and silicon dioxide here, this is amorphous, isn't it? And this is crystalline. If I look at the interface, let's assume that this is perfect lattice like this. Okay, silicon lattice, distances are all fixed, and this guy has, let's say, one oxide, some oxides like this, and in between some silicon atoms, silicon bonds are there like that, no? Something like that. I'm just trying to say this is an amorphous material, and so on. You see the point? So when you have an interface between amorphous and silicon crystalline materials like this, there will be some things, where there is unsaturated bond. For example, this silicon doesn't have a bond, and so on. Okay, there'll be what do you call it? Dangling bonds. Dangling bonds exist at interface between silicon and oxide. Okay, it just turns out that silicon dioxide means it's very good interface. But if you have other materials like high K and all that, there can be much more dangling bonds. So there is an issue. There will be greater lattice mismatch and so on, right? So there are some issues, technological issues, which can actually, spoil this. So there will be some defects. This is at the interface. Even in the bulk of the semiconductor, there can be defects. For example, if I talk of an oxide, let's say silicon, and then there is a dielectric on top, it can happen that, when you apply a voltage, let's say we are applying some voltage on the top here. Let's say this is VG, and VG is 1 volt. Okay. And there are some electrons here, right? Let's assume that there are some negative charge on this side. What prevents a negative charge from actually getting into the oxide and sitting there? You can have a trap within the oxide which kind of collects these negative charges. Okay. If they enter and get trapped, electrons get trapped inside, it's a problem. Okay. Similarly, holes can get trapped, and there's a lot of physics that we study. Okay. So there's a lot of more detail to it. It's not necessary at this stage, but yeah, these things will always be having some improper oxide. Okay. It's not perfect. Right. It's interesting to think about what happens if you have some charge, right? What happens at threshold voltage? Right? Think of that. Let's say I have a MOSFET like this. I'll make my life a little bit simpler. I'll say somehow, the oxide fabrication was imperfect, and because of that, there are some positive charges trapped in this oxide. What will happen to the VT? Now, when compared to VT, VT of a pure device. Okay, what will happen to VT?
Will it increase?
So, if you have positive charge trapping, essentially you can say that these positive charges will also cause some inversion charge to happen. Correct? These are fixed inside the oxide. Okay, let's assume that they're fixed inside the oxide, and these positive charges will actually cause some inversion charge to appear. You agree, Akshay? Akshay?
Yes, sir.
Yeah, if you have some positive charges here, they'll lead to some negative charge on the interface, right?
So it will be lower.
Lower, yes. The effective VG can be lower. Okay.
Yes.
Yeah, positive trapping, positive oxide trap charge. I think we had some problem also in this. Charge will lower VT of an NMOS device. If it's a PMOS device, opposite, because it will repel the. Okay, Bhunesh, I know you typed on the chat, and I think I was just trying to finish this and come to your question. But anyway, you came on this. Okay, yeah, all right. So I'll get to that question. Okay, thank you, Bhunesh. Just give me a minute. Okay. So so now you'll have a lower VT because of this MOS device. Lower VT for an NMOS device or a PMOS device. Yeah, I hope I gave you a long-winded answer. I'm just trying to cover a lot of material. Yeah, all right. Any Bhunesh had a question. Let me switch. Actually, I think did I answer your question, right? I think I answered in a very, very long way.
Yes.
So that everybody's on the same page. That's it. I took some time. Okay, Bhunesh had another question. Can you explain in a MOSFET operation how body terminal affects amplification? Amplification, Bhuvnesh, I mean, what do you mean by that? Now you have revealed yourself, ABC.
Sir, actually, sir,
Ah.
when we gate terminal is grounded and drain terminal is we are giving more supply voltage. Can we change the performance by just grounding the body terminal also, sir?
Yes, it will definitely affect the temperature, affect the operation, Bhuvnesh. Okay, we can think about it like this. Okay, so essentially you have an oxide here, no, on the top, and then there is a metal on the top here, right? This is my metal VG. Now the question is, so far we have considered only. We said VT is effectively, this potential across this. What is the voltage drop across this that matters, and you can have some charge here is what we have been saying. Okay, but another control on the MOS device is through the body. Okay, so basically you have the source, drain, gate. There's a body here, bulk or body. Now the important thing is you will have a junction here, isn't it? You all agree that there's a junction, 2 PN junctions here? Bhuvnesh? Let's say this is an NMOS device, so I'll call it a P-type substrate, N plus, N plus. So basically you have N and P, right? PN junction here at these interfaces. You have this
Yes,
PN
sir.
junction. When you have these PN junctions, this is necessary. You also know that, no? Because if I try to draw a band diagram across this here, right, at this interface, at this line, along this line, just below the surface, essentially you have both sides N. So let's say I'll put it like, let me put the Fermi level like this, EF, and I have my N plus and N plus. This is my source. This is my drain, and in between I have this sort of substrate. This is my bulk or body, whatever, substrate, a channel in this case. I'm drawing only at the channel. Okay, so effectively what's happening is, this is a picture. You see that this is, okay. So I'm talking about the line in this line I'm talking about. If I talk about the band diagram, it will look like this along the line, okay, along channel, source and drain line. So now, because of this, the electrons cannot flow. Okay. Now, if electrons cannot flow, the current will not pass. Now, when we apply the gate voltage, in effect, what we are doing is, okay, this, if I apply VG, apply plus VG, positive VG, then effectively you get to a point where this is your source drain, and then now the substrate, the barrier reduces. Okay, and we call it inversion because this is a P-type substrate, right? In the channel, now channel went from P-type to effectively N-type. Okay, we call it inversion, but in the energy band picture, you will see that the bands have become, the bending has become lower, and then you have less barrier. Okay, so current will flow. Okay, this is on state of MOSFET, and this is off state. Now the question is, you see, where is the PN junctions in this band diagram? This is my PN junction. This is another PN junction, correct? Now the PN junction essentially is becoming forward biased, and you have more current flow. So across this junction, the depletion width reduces, and then effectively you have more current conduction. Now, if I apply, let's say, negative voltage to this, what happens if negative voltage is applied to bulk or body? Okay. One effect could be, if let's say I think of a situation where this is grounded and this is positive, this is ground and this is positive, then the reverse bias increases. Okay. In effect, less of current conduction will happen. So we say that when this happens, PT increases. increases. Okay. How much that happens and all that we can compute. Effectively, it turns out that, this is called basically the body effect. Okay. VSB, if you apply different voltage between the source and the bulk, and you will effectively see that the threshold voltage can increase. You can also think about it another way. You are applying negative voltage here. Effectively, you are repelling the electrons, and then we are making them go towards the well. VT should increase, isn't it? If I apply negative voltage to the p-type substrate with respect to the source, my reverse bias increases, and then I'll
Hello, sir. Hello.
Hello, can you hear me? Hello?
Yes.
Okay. Just we will wait. I think you will reconnect. Hello, sir.
No.
Hello, guys. Can you hear me?
Yes, sir.
Yes, sir.
Okay. Yeah, my screen is shared.
Yes, sir. We can see your screen.
Okay, good. I don't know. In my case, I'm okay. Yeah. So, did I answer your case question, Bhunesh?
Yes, sir. Got sir.
Okay, good. Yeah, I think I don't know. Mine is still not responding on the second system. Just a minute. I'll try to log back here also. I don't know what happened. No audio from. Okay, now I think Hemant also can hear. Yeah. So I was talking. I'm still audible, right? Sorry about that. Multiple confirmations. Good. Yeah. So what I was saying is.
Sir, but your screen is not shared.
Yeah. Okay. Fine. Wait. My screen, I thought I was sharing. It went. Okay. Yeah, that's what I thought. Now I think it's okay.
Yes.
Good. All right. So Hemant was asking a question. Hemant was saying that it's a digression. He said, but can you get into MTech at 28 years old, 28 years of age? Well, Hemant, it doesn't really matter. Age is not a question at all. Nobody cares. They just want somebody who can work on some things, and for that, fundamentals are necessary. So if you are hardworking, I don't think there's a problem. Okay, you can always get into an MTech. But one thing, Hemant, I'm not meaning to discourage you or anything. I don't know. You might actually be working still, and then that's why you didn't give gate or whatever. But I can tell you from personal experience that if you delay it, it becomes harder to concentrate. It's always easy to study at young age. Okay, even if I kind of overload, you can take it when you're young. Okay, no, I should not say overload, but when I remember, when we were in the college, in the first, in my MTech and all that, we were literally not having any, breathing space, in the sense it was so packed. We had assignments, homework, so many things that you can do it better when you are young. Okay. As you grow older and older, it becomes harder. Unless you are incredibly motivated, it will be hard. Okay. So that's okay. I mean, but having said that, I have students in my class who are actually above 45, maybe. They are even older than me. Okay. And that's okay. You don't care about age and all that. Okay. All that matters is enthusiasm for learning. I know of people who have started doing their PhD at 65. So yeah, if you have that passion for learning, you can always learn anytime, any age. Okay. That's the question. That's the answer I have. And any other questions, guys? I think Akshay had asked a couple of others. I'm sorry, can somebody read for me, because I'm not seeing it right now.
Yes, sir.
Yeah.
Sir, one question is, how significant is the effect of spin on the flow of current in MOSFETs? Or does it have any effect in a?
Okay, how significant is the effect of spin? Well, okay, spin, first of all, is not a, it's not not a very well understood topic. I mean, no. I mean, it's a more slightly less intuitive topic, at least for me. Okay, but in a modern MOSFET, I think essentially you have both spins in the carriers. There's an equal distribution, so spin is not really at play. If you really want to look at how the spin impacts, we'll have to create these spintronic devices, and for that you have to have spin injection. We understand that there is a spin half, plus half, and minus half. That carriers with the different spins are getting injected into the channel. We can have a spintronic device based on that. But the issue is, we'll have to work with magnetic materials. So iron, cobalt, nickel sort of materials. You combine them, and then you can actually have use them for actually logic. Okay, it can be done, but in the MOSFET devices that we are studying, I think spin is not really at play. Okay, because effectively you have equal spins, electrons, and it doesn't really manifest. Yeah. Okay. Okay. Yeah. Hemant, don't worry. I mean, it's okay. See, I myself have done MSc, I have done an MTech, then I have done a PhD. I have taken a very long path. Okay. Sometimes it's okay. Everybody is, they have to figure out what they like and what they want. That never goes waste. Don't think of it like a wasted time. It always is useful. You learn something more. And eventually it's not a race. Nothing, right? Life is not a race. We try to learn and we do. That's whatever we like. That's it. We should be happy in life. Whatever you do, that's okay. Yeah. Okay. Any other question from ABC? Okay. Bhuvanesh.
Hello, sir.
Yeah.
I have some three-part question, sir.
Okay.
First is, when there is an inversion where the P, let's take an NMOS with P substrate.
Okay.
So when there is an inversion, so we clearly know that P substrate majority is holes.
Right.
So when a channel is created, where that extra electrons are coming, sir?
Oh, that's fantastic. That's a great question.
So first question. Second question, sir, that during pinch off, that our channel is clearly tapped off.
Yes, correct.
So how we getting a current, sir? It is acting as a constant current source. If there is no channel, how they will hell getting current, sir? That's second question.
All right.
A third question is that I'm a PhD scholar, sir, and currently doing some work in FinFET. Is there any scope, sir?
For what?
In FinFET,
Of course. No, FinFETs are the current devices. Why not? Yes, of course.
Okay, thank you, sir. That's
and don't think of the areas and am I working on FinFET? Am I working on MOSFET? No, all of them are electron devices. In fact, I'd even think of optical devices as optoelectronic devices. Okay, it's not about whether you're working on specific things. You have to understand the underlying ideas. Okay, once you understand, you can apply it to various different things. And also think about it, Bhuvanesh, your career is going to be 30, 40 years long, and technologies are going to change. You don't know what technology is going to be there 10 years from now. How can you prepare for it? And education is not supposed to teach you, only the current latest things. It's supposed to also teach you to survive after 15, 20, 30 years. Correct? And at the rate of technology, nobody had, how many people have heard about a FinFET, in 1990? Okay. So, yeah. So don't think about in those terms, do I understand electron devices? Do you understand optoelectronic devices? Then you understand a lot, man. I mean, you can apply that to various different fields. Okay. In fact, I mean, thinking of career choices, because Hemant, you are the one, right, who was mentioning, Hemant was mentioning that, career choices. Now there is this India Semiconductor Mission, and, government really wants to incentivize semiconductor manufacturing, because, we are actually spending a lot of money on buying semiconductor devices. So look up India Semiconductor Mission. They're trying to push it hard, and some companies have started. Foxconn along with Vedanta is doing something in Gujarat now, I think. There's some other proposal in Mysore state. There are a lot of packaging proposals, one in Hyderabad and a couple of other places. So a lot of things are happening, and I hope that, we are at a threshold of a great revolution. I am optimistic. I would like to continue that. I would like to continue believing that. Let's see how it goes. But I think it's always, if it succeeds, I think we are in something like, in software in 1990s. If it succeeds, I think we have to make it succeed. India cannot be a superpower by being dependent on so many things, chips for some other countries. We have to manufacture, and we have to understand. We need people who will understand all this. Okay. So, I think we are on that threshold. So I hope that it will pan out. And we should always be optimistic in science anyway. We can't solve all the problems, but at least we understand and try to think about them. All right. That was a short interlude from my side, Bhunesh. So the original question was, sorry?
So the question was Lakshmi, sir.
Yeah.
The question was asked from Lakshmi, sir. I am Bhunesh.
All right. Okay. Sure. Yeah. So,
I have two questions.
Okay, fine. Good. Okay. All right. So, yeah. Okay, good. Okay. So the question was basically about MOSFET, right? Where are the inversion charges coming from? We all know that there are p-type carriers, right? In an NMOS device, it's a p-type substrate. To paraphrase or to exactly quote Lakshmikant's question, where the hell are electrons coming from, right? Well, you don't have to go to hell for that. Electrons are already there in the semiconductor, okay? So this is a p-type, okay? Bhunesh, that's why it's subtle. I mean, don't worry if we talk about MOS capacitor, right? In the 7th and 8th week, we talked about the MOS capacitor. So we consider this structure, metal, oxide, and semiconductor, MOS, right? So we dealt at length with this, and don't worry, this is the heart of all the MOSFET. So now you're right, there are p-type carriers, majority p-type. So and A is, let's say, 10 power 17. Okay, so your P is going to be 10 power 17, N is going to be 10 power 3, roughly, approximately, right? I don't want to do the exact calculation. Ni is 10 power 10. Okay, everything is centimeter cube per centimeter cube. So now what we are doing is, there are still some electrons here. The important thing is to realize, if I drew these charge diagrams, in the MOSFET. Okay, I said, you essentially have, if you think of this is 0, this is my TOX. I have a, let's say, positive charge on this side, on the gate side. And I said there is going to be a negative charge on the opposite side. Right? This is what I have been drawing. Negative charge, and this is positive charge. This is gate. Right? This is gate. And it isn't balanced exactly. I mean, in this diagram, it's not balanced, but the overall amount of charge has to be balanced because it's a capacitor. If you have a capacitor, you have a plus Q and a minus Q, they have to be balanced. Okay, if it's not a leaky capacitor. If it's leaky, what happens? Anyway. All right. So now, Bhunesh, this is what? Not Bhunesh, Lakshmikant. What is this region? This is a depletion region, isn't it? Okay. If it's a depletion region, what happens? We studied in the non-equilibrium situations in week 6, I believe, right? We talked about non-equilibrium situations. We said that if you try to take semiconductor out of equilibrium, for example, you deplete it, it'll always try to come back to equilibrium. Okay. It'll come back to equilibrium by actually generating electron hole pairs. Okay. So when you have a depletion region, it tries to come back to equilibrium by EHP generation. How will the EHP generation takes place? Go back to week 2 or 3. when we talk about basic doping and all that, we talked about it. The bonds, basically, the bonds between silicon atoms will break, creating an electron and a hole pair. Okay, and then there is a balance. You create electron hole pairs, and then some of them will recombine. Eventually, there's an equilibrium, and that is what we are calling as Ni. When we say this Ni, it is dependent on temperature. We said no. That is because there's an equilibrium between bond breaking and electron hole pair recombining. Okay. So anyway, in this case, what happens is, Lakshmikant, do you agree that there is electric field in this region of space? Lakshmikant?
Yes, sir. Yes, sir.
There's an electric field, right? What?
Yes, sir.
Positive or negative?
Yes, sir.
Positive or negative? If I draw a band diagram, what will be my electric field? If I draw a band diagram, it looks something like this. Okay. This particular thing, right? So you will have like this, and let's assume that we have not completely inverted. Let me change this a little bit. Like that. Now we have depleted, right? But there is an electric field which is going in this direction. E field in positive direction. If there's an electric field in the positive direction, what happens? Whenever you have electron hole pairs, in this region, they basically electron hole pairs are generated. EHP generated, and then there's an electric field which will cause the holes to go in this direction. Holes will go in this direction. Electrons will go in this direction. So electrons which travel towards the interface will create an inversion layer. Does it make sense, Lakshmikant? This is a MOS capacitor. If you have a MOSFET, you don't even have to wait for electron hole pair generation, because you have two huge reservoirs of charges on the sides. They will flow. Electrons will come in from there. Okay? And they will try to supply the electrons. Okay? That's why if you look at a HFCV of a MOSFET, go and look back at the CV of the MOSFET, okay? And then try to understand what happens. CV of a MOSCAP will be different from a CV of a MOSFET. Think about it. Basically, it's much more difficult to get a HFCV in case of a MOSFET. It looked like a LFCV all the time. Because you don't, HFCV, the curve CV stays slow because you are not able to generate the electron hole pairs in sufficient amount of time. Okay. In LFCV, it goes back up. But in case of MOSFET, you'll have a supply of electron hole pairs all the time from here. So the CV will be different. Think about it. Anyway, I talked about it also, I think, in the class. Let me try to Akshay had another question, I think, right? Guys?
Yes, sir. Yes.
What was the question?
Sir, can you hear me?
Yeah, I can hear you.
So the question was like he wanted you to provide him with some external links for to read about the technology notes, and also like can you discuss a bit about the next paradigm change that gate all around FETs will bring to the industry?
Okay, so links. Well, there are no textbooks, Akshay. There are no easy links. These are evolving technologies. And I put some links in my slides on week 10, I think. When I talk about the MOSFETs in 21st century or something, I called it. Because generally all the semiconductor textbooks talk about the past things. Okay, there are some things I added into that. The best resource for these things would be to look at these presentations by Intel and AMD and so on, all the semiconductor manufacturers at places like IEDM, International Electron Devices Meeting, that is organized every December. Okay, that's where the latest advances are discussed every year. So there'll be some live sessions, and there are now some technology blocks as well. For example, I think I came across something called semi-analysis. It's actually run by a guy by name Dylan Patel.
Yes, sir, even I follow him on Twitter and on LinkedIn.
Okay, I see.
Dylan Patel and Daniel Nenny of SemiWiki.
Okay, nice. Yeah, exactly. Yeah. Akshay, what do you do?
I'm an undergraduate student.
Yeah, undergraduate. It's nice, man. I mean, I'm happy that you are so interested. I'm really happy.
I'm like mad about all this. I mean, the reason I took up electronics and communication was sort of inclined towards electromagnetism in my 11th and 12th standards. So I thought of I could study a lot more about the physics aspects of it in my EC curriculum, but sadly, communications is a lot more math than actual physics. So I ended up getting disappointed with EC. Then MOSFETs gave me the new hope, some sort of hope to take up, and actually that got me interested in going ahead like crazy.
Very nice. No, if you're interested in physics, actually, we also do a lot. I mean, I have a parallel course on nano and quantum photonics, I call it.
Yes, so one of my friend actually took up your course and he's like, I'm unable to bear all those terms, and he's like has been listening to all those terms for the first time. So
yeah, it's harder. No, but anyway, this you should not. I think first time, right? When you take all these courses, even this particular semiconductor course can be too much. I try to pack a lot of it because I try to cater to a wide variety of audience. But I think you should not try to understand each and everything at first stage. It will take me a couple of iterations. Believe me, I have taken all these courses, and then I worked a couple of years and all that. But still, when I start teaching, I still understand them in a greater detail. It's not that everything you understand at the first thing. You understand a couple of things slowly, over time you'll understand. Yeah. So, which college are you studying, Akshay?
I'm in PS University, sir, located in Bangalore.
Yeah, I know. Okay. Nice. No, there's a lot of interesting things. And Akshay, if you want futuristic, there are a couple of things about anyway, quantum nature of light and all that. So a lot of interesting things going on. Yeah. Okay. All right. Somebody had a question.
So I'm also involved in research with a professor in my university.
Oh, very good. Very nice. Very nice. Good.
It's based on density function theory, use of material modeling.
Okay. You're calculating what properties?
Kind of now, I'm still in the start. I'm still in the starting stages, so still there's a lot to learn and use open source platforms.
Of course, yeah. Ab initio, right? You're using, yeah. Okay, good. Very nice.
Sir, I have a question. Sir, in inner breakdown and avalanche breakdown, both these band diagrams are similar, sir. How can we differentiate, sir? This is the first question, sir. Again, in MOSFET, we have two mass capacitors, sir. How can we do this with BJT, sir?
How can you differentiate mass capacitors and BJT, sir?
No, sir. We have two mass capacitors in MOSFET, sir. How can we correlate this thing with BJT, sir? Similar, we can have two PN junction.
A BJT is two PN junctions, okay? And I mean, that's all. You can under P and so you have two types of BJTs, right? NPN and PNP, right? NPN and PNP, right? These are essentially two back-to-back PN junctions, nothing else. Okay. Of course, there's a lot more transistor physics you can understand from BJTs, but I deliberately didn't cover it in this course because I feel that it's a small area. It's an interesting area, no doubt. But at least in the current technology, we don't make so many of BJTs. Okay. We use them for high-speed devices. And there are things like bi-CMOS, they call it. BJT plus CMOS combined. There are some technologies for that. And, especially in the RF, right, where you want high-frequency devices. Your Wi-Fi or cellular communication devices are roughly 1.8 gigahertz and 2.4 gigahertz and so on. So you want slightly higher than that. So for that, you need this BJT devices, okay? But the problem is that they are very leaky, okay? That's why they're not good for logic. The on-off ratio is not that high for these things, okay? And that's why we don't like them for for digital circuits, okay? So yeah, that part is easy. That is the difference between how do you differentiate between PN junctions and BJTs. Just looking at the thicknesses and so on. There are some more criteria. For example, the base has to be thin, okay, and then the emitter has to be highly doped. If I call this an emitter, right? Emitter, base, collector. This has to be highly doped. This is moderately doped. This is low doping, and so on. Okay. So there are some constraints, because we want a transistor action. So effectively, what's happening here is that you have a IE, okay, and there is an IC, and there's an IB. Okay. So the emitter current has to be equal to IC plus IB, the base current plus the collector current. But in effect, what happens is if you control this, put a resistor and control the base current, you can control actually much larger current. Okay. So through small changes in the base current, we can actually affect great changes in the collector and emitter currents. So because of that, that's a transistor action that we talk about. The issue is that there is still some current which is non-zero that is flowing in through this, so it's going to bleed power. Okay, that's why we don't like it for digital. So that's the easy part. The other part, first part, if you can just tell me one more time, MOS capacitor, how do you differentiate with? You have PN junctions in MOS capacitor also.
BJT.
Yeah, okay, yeah. BJTs also, you have 2 PN junctions. Yeah, that is it. 2 PN junctions back to back, and there's some thickness. So it will be very interesting. I teach it. I mean, in IIT Hyderabad, sometimes I teach. I put in some band diagrams for a BJT. Okay, it's actually fairly simple. I mean, if you understand the concepts of diodes and all that, you can understand. Okay.
So here, in MOSFET, we have impedance. So similar with emitter and in MOSFET also we have output resistance R0. Similarly, how we have resistance here, sir, in BJT. Between source and drain, we have a resistance, sir.
No, we don't talk of source and drains in the BJT, but of course there's going to be some resistance. If you look at the IV characteristics, right? In BJTs, it becomes a lot more, dependent on the biasing characteristic. Whether you're doing common emitter, common base, common collector, the biasing characteristics will be different. Okay, and the resistance also will be slightly different, of course. Yes.
No, sir. What I'm asking is actually we have resistance in both source and terminal. Source terminal and drain terminal, we have a resistance. Similarly, how can we correlate with BJT, sir? Will there be a resistance between emitter and collector, sir?
That's what I'm saying. You have to think about what sort of configuration we are using. Are we using common base, common emitter? Basically, you have 3 terminals: base, emitter, and collector. So we'll keep it common between input and output. Let's say if you take off common base, right? So you'll have a voltage here and resistance, and there'll be another voltage and resistance here. So this is a common base configuration. Base is common to both input, output. This is output, this is input. Okay, like that. If you have common emitter, then you'll have, depends which is output, which is input. So you'll have to understand how it's a little bit, you can read it in any textbook, standard textbook, I think. So you'll see that if you understand PN junctions, you will see the details of it very easy. Okay.
Okay, sir. One more question, sir. One last question.
Yeah. Tell me.
What is the question is actually avalanche breakdown and Zener breakdown. Both these band diagrams are similar. What will be the difference, sir?
No, Zener actually only happens when you have very thin junction, right? The bands are very steep. So there's band-to-band tunneling happening. That is one thing. Okay. Avalanches, basically, you have to have large amount of energy. Breakdown is still the same process. It's in the reverse bias and all that. But it's just that your carriers are getting a lot of energy and then it's breaking down. Zener occurs at smaller voltages. The avalanche occurs at much greater voltage. Zener. Zener voltages are lower, right? Zener breakdown voltages are usually lower. Okay, and the thickness of the depletion region matters. If you have very high dope, your bands will bend very steeply and you can have Zener breakdown. But if you have moderately doped devices, the depletion region will extend and you'll have carriers actually multiplying very fast and you'll have avalanche most of it. Okay. So you have to look at the doping densities, how the doping densities are.
Okay, sir. Yeah.
You understand when I say that, depletion, doping increases, the depletion width changes, right? So the tunneling across that will also be impacted. So Zener breakdown will be impacted. So I think Zener will occur at very high doping densities.
Sir, you missed out the second part of my question about how GFETs would bring the change to the industry.
Oh, GA, gate all-around transistors. Okay.
Yes.
Gate all-around transistors are actually the ideal transistors in a way. Okay. Because you will have best control on the gate, on the channel conduction, right? So I think I mentioned one of these papers in those last week 10, I think, wherein I talked about, I gave a reference to one of those Intel papers at IADM in 2020 or 2019. Okay. If you look at that, they have implemented basically a gate all-around transistor, but it's definitely an ideal structure to implement. You'll have the best control because you're surrounding the gate all around that. But the problem is fabrication. How do we connect? How do we, do all that? It involves a lot more gimmicks, a lot of, not gimmicks, I should say, a lot more advances and challenging, quite challenging to fabricate these structures. Okay. So, yeah. Okay. Well, yeah. Hemant is asking, can I take Niemann as a reference for gate? I mean, Niemann has a lot more than you require. Gate, don't think of textbooks. Think of understanding. You should read from multiple books. It doesn't matter which book you read. Okay. I mean, I would think that it depends. I don't know. Yeah. I really love Pierre more than anything else. I use a lot of Niemann in this because Niemann has nice pictures. Pierre is very old one and I couldn't get a good copy of it. So I was using pictures from Niemann. But I think Pierre is amazing in terms of explaining the physics. Okay. And I'll never say that, read one book for gate. Gate, I mean, you all know the technique anyway. Gate, the only way to, or rather one of the ways any people have done, and including me, what we have done is take the previous year's question papers and keep solving them. Make sure that you solve all the questions and understand everything in that regard. And you'll do well in gate. Gate is not a very fair exam, I think. But don't think of, don't say that, oh, I'm going to sit with semiconductor devices, I'll learn it in 2 months and then I'll continue to something else. That won't happen. Okay. You should always be open about, don't think, I will learn everything about some topic. Keep moving on. Keep taking questions, solve them very well. It's not the matter of who is the smartest and all that. It's mainly about who is best prepared for the exam. It's not about whether you can solve it in hours together, but in those limited 3 hours, how can you solve? I think if you are prepared for that, you will do well. But of course, if you are learning all these textbooks and all, it is very important because it gives you insight to approach newer problems. You have to do that. Learn. Any textbook will be fine. Streetman is fine. Niemann is fine. Pierre is fine. Don't think that you'll understand every single aspect. Niemann has a lot more other things. So, okay. Good. I think I answered this. Anything else? Saurabh? Anything on anything we left out on the forum or somewhere, the Google sheet? We have any other questions?
No, sir.
No? All right. Guys, yeah. You just, let me know any other questions you have. Write to us on the forums. Okay?
Sir, Bhunesh is saying if it is possible to have one more live session before the exam.
Of course, we will do that. I want to do it. I was tied up initially. That's why I couldn't hold any live sessions for this course earlier. I'm happy to hold it, man. I'm very happy. We'll just schedule next week again. I'm fine. How many other times you read? I mean, you keep asking questions. I'll keep doing it. Okay. It's driven by you. I'm open. You want every week, I can do it. No issues. Yeah. All right. Oh,
Hello, sir.
Yes.
Yes, also, sir, I'm extremely happy of the fact that you did your PhD at Purdue, which is one of the foremost institutes and has been involved from the times when transistor was actually being invented. And also,
Right.
you worked at TSMC and actual semiconductor device engineers handling this course.
Well, no, I should not claim any fame in that. So essentially, that would be misleading if I say that. I mean, you're right. Purdue was actually, I think it's one of the great places. There was actually a competition between a group at Purdue and at Bell Labs. Bell Labs guys, when they published this point contact transistor, they were actually in a hurry to show it because they were worried that the team at Purdue will publish it. Okay. So Purdue was there right from the beginning of the transistor. And
Yes.
In a way, if you think about it, even the current transistors, the amount of device physics and all that, some of the greatest people in that are actually at Purdue. People like Supriyo Datta, Mark Lundstrom, and then even Ashraf Alam and Gerhard Klimek. Amazing people, and you have a lot of, if you go to NanoHub, there's so much of resources for these things. Okay, I think they're getting old, but still, I think they're amazing. Okay, so if you look at any of those lectures, Supriyo Datta especially and Mark Lundstrom, they make it so simple. Okay. So yeah, I mean, that was that. And at TSMC, I didn't really do, I developed characterization techniques. I was not involved in the device design, but I have some idea of it. That's all. Yeah, I can't claim anything more than that. But I love it. I mean, I get excited by it and I'm happy. I want to see, I am also kind of a little bit not happy that in general in India, right, everybody wants to do software. Yeah, sitting and writing code, you can write it, but we should also be able to make it. So I want to excite more people into semiconductors. That's my, that's my only goal. That's why I'm very happy to interact with you guys any number of times you need. That's why I'm saying, even if you want one-on-one, we can talk. I'm happy to interact with you. Any questions? Tell your friends, get them enrolled. Let's get it excited. We need to make India, like what government was saying. We need to make India a semiconductor nation, and for that we have to interact with people at all levels. And we should not, we should have people who are not scared of taking up challenges. Oh, it's so complicated. I've never heard of quantum mechanics. I won't touch it. No, it's not. Things will become simple over time. When you started walking, you fell so many times, but you learned walking. It was so difficult to read. I mean, your parents would tell you how difficult it was for you to write a single word. You wrote it. Over time, you will learn it. It's not that we should not expect that I'll learn it instantaneously. It's the first course I have taken. If you sincerely commit to it, give some time, let's say 5 to 6 hours a week, you can learn any subject that we're offering. It takes time. You cannot learn these things without committing time. Okay. But at the end of it, you'll find happiness. I mean, you'll find, if you're working in an area that you love, that's great. Yeah. Okay.
Yes.
Yeah. All right. Okay.
Professor, could you tell a bit about your experiences with research at USA?
Let's do it in a different session. Okay. This is semiconductor devices. We can do it separately. Okay?
All right.
If you're interested in the research aspect, go to my webpage. There is a links section. Okay? There are some interesting tidbits about what research is and all that.
Yes, sir. I looked at dielectric nanophotonics, silicon photonics.
Sorry, you want about silicon photonics and so on?
Yeah, I looked at your page.
No, there is a links section in the bottom. Okay. Graduate school, graduate school survival guide or something like that. How PhD happens and so on, and what kind of research experience in Russian, this one, what it was, and I thought some interesting things about there is a paid PDF on Bell Labs scandal. Okay. I think these are some interesting documents you can read and you'll understand something. Yeah, I mean, we can talk later. Yeah. Okay, sure. Because I think now we are running out of time. I think Balaji will also have another session to manage. Okay. Isn't it, Balaji? We'll again meet next week. Next week.
Half an hour time we have, sir. No, we can.
Oh, okay. We have time. Then I can go on.
We have time.
Okay, fine. So yeah, tell me, Akshay, so what was the question I can answer? Yeah, let me see.
About your research and all that stuff of what happens beyond undergraduation.
Oh, okay.
With respect to semiconductor devices.
Okay, so see, one of the things, right, in semiconductor devices, we have been talking about scaling and all that. Now we have come to very, very small dimensions. Okay. Now I think as such, the device scaling is not the main bottleneck. Okay. For example, if you look at, let's say now the way the power is, getting consumed in the chip, one of the important aspects is how do you get the signals off the chip? Okay. You need I/O, right? We call it, let's say you have a chip like this. You have a chip. And then you're trying to connect that in a board and all that, no? So you want these electrical signals to come out. Okay. Now we have packed so many chips and already density is quite high, but it still has to interact with these peripherals like the memory and so on, right? Memory and all the other devices that are there. It has to interact, right? The processor. Now, electrical I/O cost is increasing quite a bit. Electrical I/O power budget, right, is increasing quite a bit. Is consuming more power. Okay. So what's happening is now, and also, we are not able to, we have multiple core processors. I talked about it, I think, in the course also. If you want to increase the number of processors further, the challenge would be, the RC delays in the MOSFET, or rather, on the chips, right? These wires essentially are limited by R and C. You can't make them too small. If you make them too thin, the resistance increases. And if you make them too long, there's a capacitance associated with that, which is distributed capacitance. And so these distributed RCs will finally impact your speeds. Okay. So for example, if you make an inverter circuit, if you look at the device itself, it can work something like 15 picoseconds response delay and all that, we can make it happen. But the processor will never work at that speed, because by the time you have a wire that connects and sends the signal across to other parts of the chip, the speed is compromised. Okay. Now, one of the important directions people are trying to look at it is, can we make optical interconnect? Okay, people are really trying to do it, optical interconnect. Okay, and all this is where the photonic integrated circuits come in and all that. Okay? That is, they want to integrate these optical devices onto the chips now, or not, or rather on the chip, at least on the system, on the package level. Okay, they want to do that. That's one direction. And even like, one of the great differences that has come about now is, it's been always planar for a long time, planar technologies, right? Now we are going into the third dimension. So they call it heterogeneous integration and three-dimensional, okay? 2.5D and 3D. So instead of, let's say, especially in the DRAM community, this has happened. Originally, let's say the memory is all in one layer. Now we are stacking multiple layers of one on top of each other. Okay. When you have these multiple layers stacked on each other, you can have much more density of memory here. Now Micron is building something like 100 layers of memory, one over the other. Okay, they have to be
the recent one is around has 232 layers or something.
Oh, 232. Okay, then you are. I mean, I didn't. Yeah, 100 I've heard. Hundreds I have heard. Yeah, basically you are stacking one over the other, right? Of course, the main thing is now you see the innovation is not happening in the device itself. Because I think device, how much more smaller can you make, right? One of the fundamental problems, Akshay, think of even the planar MOSFET. You're having, let's say, the active area, let's say this is 100 or 50 nanometers, okay? And this is, let's say, some 50 nanometers, just, or 100 by 100, let's consider. 100 nanometers by 100 nanometers. I'll consider an area, active area, okay? So basically the source, this is my length of the transistor, and this is my width of the transistor, let's say. You're looking at it from the top. Okay. Now, how many dopants are present here? It will be something like 50 to 100 dopant atoms. You follow, Akshay? We are talking about, let's say, 10 power 17 or something. The density of silicon atoms is 10 power 22. Effectively, one dopant in 10,000 atoms. And if you look at the area of this, surface area, basically the dopants are randomly located now. Okay, and there is no way we can control that. When you do an implantation step, you will get various locations. The dopants itself are very located. Now, depending on where exactly my dopant atom is located, my VT will be slightly different. There will be the fluctuations in the devices. Correct? You follow what I'm saying?
Yes, sir. Yes, sir.
Just try to compute it. I mean, I've done it at some point. I think it will come to about 50 to 100 atoms or something like that. So even the atomic positions becomes random. So you fabricate two devices next to each other. You might have different dopants, and then there will be some fluctuation in the threshold voltage. Okay. If you try to make it smaller, the variability increases. Okay. And then how can you design with that variability? All of this industry is built upon this bedrock of precise models. Okay. With so much of, if you make 1 billion transistors and all of the IV characteristics are more or less similar, or, close enough at least, we have within the noise margins. Okay. But if you push it too far, how do we get it? I think there should be a paradigm shift in this. Okay. Maybe we evolve from this classical, von Neumann architecture to something called neuromorphic architectures and all that, where you try to bring memory also closer to the compute. That is one thing people are pursuing. And various other things. I mean, honestly speaking, nobody knows what is going to happen. You look at the IRDS roadmaps, everything is mentioned in that. Okay, what exactly will happen, we don't know. We try to understand all of it. Okay, and see as the technology progresses, some solutions will work out, some will not work. Okay, so yeah, what next? Well, I mean, that is the near-term things, right? If you want to continue electron devices, the next big thing, I mean, I don't know if it's going to happen or not, but quantum computing. Okay, that's the frontier. There are some very simple, elementary, few bit or few tens of bits quantum computers built now. They are bulky, they are like ENIACs, they consume huge amounts of power, and all that is happening right now. But what if we are able to miniaturize them? Maybe we don't need to sell a quantum computer to every household or every phone. Even if you make one for every country, or 2, 3 per country also, that probably is enough. And we can solve a lot of interesting problems with that. Okay. So, I mean, yeah, we don't know that we evolve over time. and we play our role and we try to learn as much as we can and we work at the frontiers, and that's it. We can't decide, many of the students tell me, oh, what should I study to get a job or what? You will do something. As long as you are doing whatever you're learning well, you will find a job. It doesn't matter what area you're learning, you have to do it very well. You have to be excellent. You have to have that passion for that. You should lose sleep on that. You start thinking, oh, what is happening? You should enjoy it. If you're enjoying it, I think you will do well. Okay.
Sir, one question, sir.
Yeah.
I'm sir.
Yeah.
Drift is due to electric field, right, sir? When we apply a field, there will be a drift. But is there any other case to cause drift motion, sir?
No, I mean drift. See,
only causes only electric field, sir.
Sorry.
For drift to move, the cause of drift is only electric field, sir. No other motion, no other cause, sir.
Drift, you need to have an electric field, yes. No other cause. Carriers move because of diffusion as well. There's a concentration gradient, but we call that as diffusion.
Yes, exactly, sir. But
yeah.
I'm asking only for drift, sir.
Okay. No, if you put it in a magnetic field, it's going to move again in response to magnetic fields. Currents will change. But if you exclude that,
okay, sir. Okay.
If you project a carrier with a velocity, you can apply Lorentz law and figure out how the carrier trajectory will be in the presence of magnetic fields. That will also cause a carrier to move, but it's very, very weak anyway, and we can't apply that easily magnetic fields and all that. So we don't worry about it. Yeah.
Okay, sir. Okay.
Okay. All right, guys. Thank you so much. I enjoy talking like this. I want as much interaction as possible. Okay. So yeah. If you guys are interested, sorry.
I've been following the roadmap that was given by IMEC, and that included GFS will be introduced around 2025-26, followed by CFETs and then the 2D atomic channel transistors. That was one of the reasons why in the previous videos I asked you about the 2D materials replacing silicon.
Yes. See, the thing is, nowadays I think I think I can't answer this online. Okay, in a live session, we'll talk separately. Okay. I mean, you also wanted to know a little bit about the research. We'll talk separately. Okay. I don't want to do it on a public this one. Yeah. Okay. So, yeah. I mean, by the way, guys. I mean, if you guys, you approach and if you are try to go and visit some places. Actually, if you're in Bangalore, you can try to go and visit IISc where some of these clean rooms are there. I'm sure somebody will oblige.
Yes, sir. But the only way I can get into a nano fab or interactive teachers is to do internship. Is pretty hard to actually get a internship opportunity under them.
No. See, what you do is you befriend your TA, Samadhan, or who is the other guy who are doing PMRFTS. One of them is at IISc.
Soham Lagote.
Huh?
Soham Lagote.
Soham Lagote is at IISc. You just ask him, can I just visit? Forget internship and all that. He's there. He can just show you. You just spend an hour. No problem. Right?
Sure, sir. Sure, sir.
I mean, if clean room is a thing, you are always, welcome to IIT Hyderabad. Okay, we can show you. We don't have IISc things, but we can show you. Yeah. Okay. All right. Okay. Thank you, guys. Thank you so much. We'll again schedule it next week because I want to do it for the other course as well. I'll try to do it again maybe next Friday or something. And then once I'll do for the other course. Okay. Thank you so much.
Thanks a lot, sir. Today's session was very much interesting.